And I would like to introduce you Kamil Adamczewski from ETH Zurich, who will talk today about the artificial intelligence and new framework to understand the black box neutral networks. Kamil, the floor is yours.
Hi everyone, I'm trying to share right now my,
We still see the other stuff.
right, what about?
Yeah, perfect, thank you.
All right, great. So good afternoon everyone. Thank you for having me here. My name is Kamil Adamczewski. I'm a PhD student at ETH Zurich and Max Planck Institute for Intelligent Systems. And I will take you for a short and ambitious journey to understand AI in 10 minutes. So first, let's start with a term, machine learning, which has been quite a buzzword recently as well. And it is often associated with AI, but it is not the same. It is a subset of AI, which this is how it is defined. It's basically the ability of computers to learn without explicitly being programmed. And I will give you an example of that. We'll show computer three pictures, one of Dota, and we will tell computer it's a person. And then we will show boys shits, and we will also tell it's a person. And then we will show a bird, and we will say it's a bird. And that's what computer sees, that's what we tell computer. And then we will show the picture of Pujan, and then we will ask computer, what do you think? What kind of class object is that? And ideally, we would like to get the good answer out of the computer because it never seen Pujan before. So this sort of problems have been dealt with as type of algorithm class, which is called artificial neural networks, which also have become hugely popular in recent years. The name is not accidental. They are imitating human brain, but they have actually nothing to do with the human brain. So that's kind of how the subsets work. We have artificial intelligence, then we have machine learning, and then we have deep learning, which deals with these artificial neural networks. And I will explain why it is the case in a second. So there are many types of neural networks. We have convolutional neural networks, recurrent neural networks. We have generative models, GANs, about some of which Jakub talked in the morning. However, this talk will be about convolutional neural networks, and that's what we're going to focus on. So let's go back to Pujan. And how do we actually get the answer out of the computer? So we take the picture of Pujan, which is actually a matrix of numbers, and we will feed it to this so-called neural network, which consists of layers. In particular, we have an input layer and output layer, and then we have hidden layers in the middle. And then we have all these connections, which basically are some kind of numbers, parameters. So we will take this matrix of image of numbers, and we will feed it to this neural network. And then we will do some additions, multiplications, and then we will get it into the next layer. More additions, more multiplications, and then another layer, and so on, until we get to the output, where we would like to get ideally the answer that Pujan is a person with 95% confidence. And then we can have other answers like it's a tank with 5% confidence, it's a bird with 0% confidence. So what are other characteristics of neural networks? Well, they are big. They are big and they are getting bigger. So basically the number of those layers is increasing. And that's why we call it deep, because they are getting deeper and deeper. They have more and more layers. They have more and more channels. They have more and more parameters. But there is a good reason for that, because with increasing number of those channels, increasing number of layers, it is actually getting also more accurate. So these algorithms are getting better and better the deeper they are. and hence the phenomenon of deep learning. However, with the scale, with the fact that they are getting bigger and bigger, we start having issues. So perhaps we would like to have smaller networks. Because why is that? So large networks take more computational time and more memory. Running on hardware limited devices such as smartphones, robots, drones, it might be difficult, as well as sending millions of parameters through a limited network. Also, energy cost of training those big networks are high. And we also have implicit costs of those smaller networks because we focus on quantity rather than on quality. And ironically, this trend opposes the research about the nature, interpretability, and knowledge extraction from within the neural networks. So the question is, could we get the best of both worlds? Could we get the networks which are accurate but are also smaller? And that is what my research is about. And the answer is yes. At least in some cases, we can do this. And I'll tell you how to do it. So let's start again with the convolutional neural network and see how they are actually working. So as you can see, this green matrix, it would be a picture which is a matrix of numbers. And then we have something called a kernel, which we will slide through this image. And basically this kernel is multiplying these numbers from the matrix, from the numbers from the kernel. And we will get some output, which is called convolved feature. And this will be a kind of a modified image of the input. So the image has actually three channels. So it has three matrices. One is each responsible for each color. So it's red, green, and blue. And we will have a kernel, which is also called a channel. We can also describe it, which we will basically impose on each of these channels, input channels. And then we will sum them to get an output. So in this case, we have three input channels, like in an image, RGB, and then we have one output channel. However, we could have as many channels as we want. And this output channels, it's basically the second layer in the network. And then we will keep doing it and we will keep multiplying and we will have more channels in the third layer, fourth layer, and so on. So in the first layer, we have three channels. In this case, in the second layer, we will have 64 channels, but we could have much more channels or less, whatever we want. And as you can see, here at the bottom, we have outputs of those channels. And as you can see, some of them actually look better than the others. And perhaps we would like to actually keep those that are more useful and discard the others. And this way we can actually so-called prune the network and get actually a smaller model. And that is what my research is about. And I'll show you how to do it in a few different ways. So as you can see here, there are basically the channels. Think about the channels as those nodes with an arrow. So this is a neuron in the neural network, and we will present it this way. And basically we have those channels, and we would like to remove some of them and have a sparser, slimmer network, which will be smaller and faster. So how can we do it? The first approach, it's based on actually a concept from game theory. It's called Shapley Valley. And briefly, I'll tell you how it works. Imagine that we have three channels and we want to rank them. We want to say which one is the most important, which one is the least important. So first, let's look at all the combinations where we are going to add and remove that channel. For example, imagine that we have no channels at all and that network has accuracy 10%, very bad. We'll add this one channel and then we will have increased the accuracy to 55%. So the increase is 45%, thanks to adding this one channel. In another case, imagine that we have already channel number 2, and that gives us the probability of 50%. That's the third image. And then we will add the number 1, and then the accuracy increases to 65%. So the increase is 15. So that's contribution of this first channel. And we will look at all different combinations, and then we will average it out. If the number, it's called so-called Shapley value. If this number is high, that means that this node contributes a lot, and we would like to keep it. And if this number is small, then basically we can discard this channel because it doesn't really increase our accuracy much. So that's basically how we can rank them, and then we can keep the most important and remove least important. So this is one of the papers that I wrote. It's currently under review in the conference. We can have another method, which I briefly tell you about, very briefly. It's a probabilistic method where we look at those channels and we are trying to learn the probability over them. And a channel which has probability, say 41% or 34%, would be more important than the one with 3%. And the one that has 3%, we would remove it. So I can tell you more details in the Q&A and question if you're interested. We are learning it by modeling through a Dirichlet distribution and learning by a method called variational inference. So this was a work actually presented last month at the ISTAT conference. And as you can see, so these two methods basically are choosing those different channels. And some of these channels that are good, have been selected as good, they produce basically feature maps where we can actually see some features which are also human interpretable. Those are in those red boxes. And outside, those are the bad channels, which are kind of blurry, which basically tells us that those neural networks can also learn features which are also human interpretable. And that's why, that's how we are kind of seeing how neural networks work. So I'm running out of time. So I can tell you more about all these methods in the Q&A session. We actually expanded this method to not to look at neural networks, but to look at inputs. So as an interesting example, I'll tell you about autonomous driving and LiDAR sensor, which senses the depth of an image. But basically, this sensor LiDAR, it has 64 horizontal lines, but they are very expensive with 64. And we would like to actually select a subset of these features so that we can actually get good depth estimation with LiDAR, at the same time having a cheaper one. So this is an ongoing work. It's something where we can also apply this method. So thank you very much. And let me know if there is anything that struck your attention. And yeah, the floor is yours. Thank you very much.
Fantastic talk, Kamil. Thank you very much. I really loved the beautiful visualizations and really easy to understand explanations. That was really cool. I would like to ask you, what is, in your opinion, the coolest thing that can be done in near future with artificial intelligence? So
it's a good question. I mean, it's actually I have a few more slides which I can show you what things can be done with artificial intelligence. For instance, we can detect objects, and that is very often used in the autonomous driving, where we actually want to see where the object is located. So autonomous driving is definitely one big area of where AI is being used. But for instance, there is machine translation, which we all use, and all the area of language processing is really hugely impacted also by artificial intelligence. So this is actually used recurrent neural networks or transformers these days. The driverless cars I mentioned. Speech recognition, but I think probably the biggest one is reinforcement learning, and this will be the area where there will be the most, I guess, impact, the most interesting applications, and some of you may have heard of AlphaGo, when basically an algorithm built by Google beat world champions in Go. It's a game which is much more complicated than chess, and people thought that we would never be able to, like, a computer would never be able to beat a human within the next decades, but it actually happened a few years ago. So I would say that the reinforcement learning is probably the area where that we will see the most interesting progress.
Thank you so much. We have one more question from Peter Tatkowski. Hey, Kamil, thanks for the talk. Question on my end. Does the pruning have to happen after the network is trained? That is there no way to know beforehand what nodes we can prune?
Very good question. Very good question. So, so the methods that I presented, they are used after that the model is trained. So, I mean, it has the advantages that we can take any model. I can take any model from internet and basically prune it and give you the pruned model. So uh, that's the sort of advantage. There are also I have another paper which I didn't present here, which actually does the same thing from the beginning, from the scratch. This is another probabilistic model where we are over the training. Basically, we put certain constraints. For instance, we want to constrain the number of positive weights, and then we will use some, for instance, L2 norm or L1 norm on the vector, and in this way we can actually, during the training, drive some of the weights to zero. So this is also another option.
Thank you so much. Really fascinating.